Good afternoon, everyone. Thank you for the introduction. I'm here today to present our study titled Startlr Effect Analysis based on multimodal physiological features in a fighter aircraft simulator. I'll start this presentation with the importance of Startlr effect analysis in aviation and our objectives of this study. Startlr effect often results in reduced pilot performance, inaccurate and delayed actions, and loss of situational awareness, listed by sudden exposure to intense stimuli. Our goal for this study is to define Startlr effect elicitation scenario on a flight simulator to define changes in both pilot performance and physiological variables. We also want to measure the extent to which the change in pilot's physiological variables correlate with the changes in pilot performance, but for now without the use of complex black box machine learning models. Our experimental setup used for this study in our laboratory is shown on the left picture during testing of one of our candidates. And that setup consists of a flight simulator setup and a physiological measurement setup. On the right side of the slide, you can see a detailed view of our flight display used for our pitch tracking task used in this study. Two indicators can be seen on the flight display, the commanded pitch angle indicator on the top of the slide and the actual pitch angle indicator on the bottom. The goal for the pilot in the pitch tracking task is to follow the commanded pitch angle indicator as closely as possible with the yellow actual pitch angle indicator during the whole task. And the commanded pitch angle indicator is driven by the pseudo-random signal, and it moves only in the vertical axis of the primary flight display. Okay. Our 6 degrees of freedom aircraft flight model used in our flight simulator is based on a generic canard configuration fighter, and it is similar to the Dassault Rafale, while the current used aerodynamic model is nonlinear and subsonic, and the coefficients, some of the more important coefficients, can be shown on the graphs. Our flight model is developed in Simulink. Okay. Setup for multimodal physiological measurements used in this study is shown on the left picture during testing, and it is equipped to measure EMG, EDA, ECG, respiratory data, and eye tracking data using both BioPAC MP150 system shown on the top of the slide and the GazePoint GP3 HD remote eye tracking system. Some of the captured signals during this experiment can be seen on the right side of this slide. Startlr effect caused by environmental factors and/or aircraft malfunctions might be characterized by unexpected and sudden changes of the following variables. First, physiological parameters and features when compared to the baseline, aircraft state variables, cockpit interaction parameters, performance metrics related to the operator functional state, and the emotional and cognitive states. Some of the state variables analyzed in this study are environmental parameters, aircraft malfunctions, and physiological features. Environmental parameters include wind gusts and thunder sounds, modeled as described, accompanied by aircraft malfunctions in the form of pitch trim malfunction. Measured physiological features include EMG, EDA, and ECG features listed below. Other considered state variables are aircraft state variables like the roll pitch and yaw angle or aerodynamic speed, cockpit interaction parameters, for example, the flight stick deflection velocity analysis, and pilot performance variables, which include pitch tracking error, altitude deviation, or aerodynamic speed deviation. One of the example of a flight simulator scenario not yet used in our study can be seen on this slide. It represents a flight route with a specific part of the route marked red, indicating a part where strong winds usually occur and a part where a startle stimulus can be expected. For that time window, in this example lasting for 60 seconds, physiological signals, flight state variables, and pilot reaction signals are analyzed and shown on the slide with this red dashed line indicating the exact time of the startle event onset. But for this presentation, we'll focus only on the flight simulator scenario shown on the right picture on this slide. It involves the aforementioned pitch tracking task, accompanied by 3 separate Startlr events, while the whole duration of the task is 170 seconds. Startlr effect is listed by a sudden change in aerodynamic speed due to a wind gust, a sudden loud thunder sound, a pitch trim malfunction, and a separate task for the pilot to call out a specific flight parameter from the flight display. During the whole duration of the task, pilots are asked to maintain the aerodynamic speed for the whole duration. In the future, this experimental protocol will be expanded with some generic stimuli and tasks shown on the left picture. For computation of specific physiological features in this experiment, each captured signal is divided into 3 sections at each of the Startlr events, and those sections are pre-Startlr, Startlr, and post-Startlr section. With using those sections, specific physiological features can be computed with the expressions given on the bottom of the slide. It's important to note here that in this example, participant 1's EDA mean value has a rise in the Startlr period and then a decrease in the T post-Startlr period, while the participant's N EDA mean value has a rise in the T Startlr period with virtually no decrease later in the post-Startlr period, which corresponds to the higher allostatic load. Similarly, the computation of pitch tracking index of performance can be performed. A closed loop system diagram of our pitch tracking task is shown on the top with the input pitch on the left and output pitch on the right, with the pilot and the aircraft as part of the system. Expressions for calculation of those indices of performance are given below, with the first one referring to the period between the Startlr and pre-Startlr, and the other one referring to the period between Startlr and post-Startlr. Preliminary evaluation of our experimental setup was done on a sample of 6 pilots of varying age and piloting experience, and the results of one of those pilots are shown on this slide. 3 separate Startlr events are marked with a vertical dashed line, with aforementioned periods pre-Startlr, Startlr, and post-Startlr marked in color around each Startlr event. On the first graph, both commanded pitch angle and the actual pilot's pitch angle can be seen, while their absolute error is shown on the second slide. It's important to note that the greatest errors in between those 2 signals are visible after each of the Startlr events. Aerodynamic speed is shown next, with notable changes in intensity due to the wind gusts. And another important performance metric can be considered deviation from initial altitude, shown on the next graph, as the perfect tracking of the commanded pitch angle will result in near zero altitude deviation from the initial value. Finally, the EDA signal is shown for the analyzed pilot on the bottom of the slide, with peaks in skin conductance occurring right after each Startlr event. 2 responses of physiological modalities are further analyzed for other analyzed pilot. Those are the EMG and EDA signal shown on the left and the right, with measured latencies between the Startlr onset and the peak of the measured signal. For statistical correlation analysis, 3 separate matrices are formed: matrix X of physiological features, matrix Y of aircraft state variables, and matrix Z of performance metrics. Physiological features and aircraft state variables can be seen in the middle of the slide, while the only currently considered performance metric is related to the pitch tracking error, and that matrix Z will be expanded in the future experiments. Expressions for calculation elements of those 3 matrices are given at the bottom of the slide. 11 features were analyzed, and they are here shown for one of the analyzed pilot with their values for the pre-Startlr and Startlr period. their mean values and standard deviations with the mean absolute error of the pitch tracking task shown in the last row. Here, it's important to note that every single feature had a rise in the Startlr period when compared to the pre-Startlr, with most notable ones being the EMG max amplitude and the EDA standard deviation. EMG signal is computed on the period of 1 second, while the EDA signal is computed over a period of 5 seconds. Pearson's correlation coefficient for correlation of physiological features with performance metric is computed for each analyzed feature and shown on this slide, along with the accompanying p-value. Highest achieved Pearson's coefficient is 0.51 for the EDA standard deviation feature with a p-value of 0.03. On the right part of the slide, that EDA standard deviation feature is plotted against the mean absolute error of the pitch tracking task with red dashed line indicating the trend line. And in conclusion, we have illustrated that correlation analysis of physiological feature and pitch tracking error performance before and after the simulated Startlr onset with two main takeaways. First is that flight simulator Startlr effect induces significant changes in selected physiological features and pitch tracking performance, but still on a limited number of pilots. While the second one is that correlation analysis reveals physiological features with the highest correlations to the pitch tracking error. Moreover, multi-frame physiological dynamics of Startlr effect illustrate fast EMG related response features as well as oculometric features, in contrast to the slow response features like the EDA or ECG. Prediction of pilot's performance due to emergencies should be computed on mentioned fast response features, as well as personalized resilience trait features like the cardiac recovery and resting RSA. Furthermore, approval for testing of 20 young military cadets has been granted, and in those future experiments, more comprehensive analysis should be performed, like the canonical correlation analysis or the machine learning methods. And finally, this experiential research might also be applied in future pilot selection and mental readiness training of Croatian civil and military pilots. Thank you for your attention. I'm looking forward to your questions.